development planning, reservoir static and dynamic modeling, technical support for academic research like PhDs and master's degrees, assistance in writing technical papers and publications, where industry expert led in petroleum courses. Also, we gave mentorship programs and customized training courses. We are glad to have you here and look forward to engaging session. Now, please, I would like to introduce our STEAM instructor, Dr. Jan Yusupov. Dr. Jan is a geomechanic engineer in 𝗚𝗲𝗺𝗃 with 10 years of extensive experience in the oil and gas field, covering geology, geomechanics, and petrophysics. The geomechanic experience includes pre-drill, real-time, and post-drill modeling. Experience in unconventional reservoirs, and CO2 utilization, Experience in geomechanics software, like in Litho Studio. Please let him a warm welcome.
Okay, good afternoon. Can you hear me? Thank you for opportunity to discuss introduction to geomechanics and application of geomechanics in oil and gas industry. So let's start. Let's see on the main tasks of reservoir geomechanics. The main part of reservoir tasks and geomechanics tasks are associated with drilling and exploration and exploitation of oil and gas fields. You can see the main task on this slide. This is associated with borehole stability, mud losses production prediction, sand prediction, hydraulic fracturing optimization, borehole trajectory optimization, casing depth optimization, abnormal pore pressure prediction, estimation of fault conductivity, DFN, discrete fracture net reactivation analysis. And also this can be associated with shear floor and daily surface subsidence and reservoir and seal compaction. Let's see more advanced these tasks. During drilling and during building of well, especially drilling, backreaming out of hole, wireline, we can have so much drilling events that can be associated with loss circulation, hole deviation, pipe sticking, mechanical or differential sticking, borehole instability, formation damage, casing damage, hole cleaning, and another dangerous drilling events. And geomechanics and adjacent disciplines, one of the more tools that can help us to improve the process of drilling and building of well and make this process less expensive and more productive. Please note the funnel of uncertainties and borehole stability estimation. You can see that incorrect mud, incorrect well trajectory, poor well plan, problem formations, poor drilling practice lead to excessive borehole pressure, reactive shale chemical reaction, excessive rock stress, and it leads in common to lost circulation, cementing problems, stuck pipes, drilling, drill string problems, well control, poor log, and another negative factor that lead for a very big cost of drilling and wasting of time. And let's see on the main types of geomechanics in oil and gas industry. There can be 1D geomechanics, 4D, 3D geomechanics, and application of geomechanics. Let's start from 1D geomechanics tasks. From the 1D geomechanics task, we can select reducing of drilling risk and preventing drilling events, especially oil and gas shows blowouts, sticking, caving, sand showings, tightening, slack offs, etc. Also, it can be optimizing well design and adjusting the depth of casing shoe placement, determining of optimal well trajectory, refining of geometry and properties of hydraulic fractures, increasing drilling rate, and reducing inefficient time and financial costs. So the common tasks of all types of geomechanics, including 1D, 3D, and 4D, you can see on this slide. From the geomechanical analysis starts from data audit. Data audit includes analysis of logging parameters, core parameters, well investigation data, drilling events analysis, daily drilling reports, and another all common information about well, field, logs information, and decision making about using or not using this information in further stages of geomechanics. This goes to 1D geomechanics. 1D geomechanics, this is geomechanics and modeling of mechanical properties and stresses along one of the offset well, and transferring of this geomechanical model on a project well. And after this, using seismic data, researching in depth domain, using geological model, reservoir model, basin model, we can start build 3D model. 3D model, this is modeling of mechanical properties and stresses, but it's not along one well, but this is in the volume of entire field, but maybe in the volume of sector of field. It depends on customers' needs. And we need to understand that 3D geomechanics, it's only static model, but this is information about stresses and mechanics in only one time step. If we want to know information about stresses distribution in the time, for example, from time step of beginning of development of field to time step of end of field, we need to make a 4D geomechanical model where fourth measurement, this is time. It can be discrete model for equal time steps, can be not equal time steps. It depends on our needs. So the 4D geomechanical model, this is the most important source of information in terms of reservoir compaction, change in the permeability and porosity, assessment of change in the stress formation, assessment of well productivity and water breakouts, estimation of out of zone injection information, recommendation of optimizing the operation of wells, development system elements, seal and reservoir integrity, fault reactivation, design of hydraulic fracturing, safety of safe mud weight window, and another information. And let's see on the input data for geomechanics. We can divide the main input data for geomechanics on three categories. The first category is red. This is information that in the absence of which we cannot build any geomechanical model. It includes the information about logs, including acoustic logs, especially S wave, P wave, density log, gamma ray, caliper, vertical seismic profiling, resistivity log, maybe micro imagers, core investigation, daily drilling reports, end of well report, any geological report. Of course, this can be pore pressure and XLOT measurements for calibration of pore pressure, SH mean, and another types of data that can be read. And another types of data, we can see that the orange and green, they optional data. They can be information about acoustic anisotropy in acoustic logging, determination of horizontal stresses using cross dipole, any reports for completed operation, production history, chronology of repairing work on the wells, and other information. Let's see on the typical 1D geomechanical workflow. This is workflow. In the head of this 1D geomechanical workflow, we can see the analysis of input data. It includes well testing data analysis, well log analysis, stress test results analysis, well test daily drilling reports analysis, and core data analysis. All this analysis lead to construction of 1D geomechanical model. And first step of construction of this model, this is calculation of elastic and strength properties, including Young modulus, Poisson ratio, unconfined compressive strength, and friction angle distribution. After this is a total vertical stress calculation, pore pressure calculation and calibration, near well bore stress calculation, including SH-min, SH-max, and finally, this is calculation of and calibration on borehole stability model, including breakout and breakdown gradient. Using this all calculated parameters, we can build a well section with borehole stability, make trajectory optimization, make also a well design optimization, and correct the casing shoes depth landing, build a drilling risk map, and develop the recommendation for improvement of drilling process, hydraulic optimization, and uncertainties assessment. And let's see on the tasks that geomechanics complete in the oil and gas industry. The first task, this is abnormal pore pressure prediction. You can see on this slide, and this is one of examples of application of Eaton methods on the clastic field. For defining of pore pressure on the shale sand reservoir and the shale seal, we can use acoustic logging data and another types of data that you can see on the next slide. And also we need to have a normal trend compaction. Using normal compaction trend line and acoustic logging as can see here, and having MDT parameters, we can estimate the pore pressure prediction profile and understand which mud weight must be safety for this case to avoid drilling events associated with gas showings, kicks, losses, and another dangerous types of mud weight or drilling events. Also, as an acoustic logging, we can use porosity data, resistivity data, the exponent, density for assessment of abnormal pore pressure prediction. This is a typical example of risk map. And sorry, not risk map. This is typical well section for prediction of abnormal pore pressure. We can see that in the lower parts of well, we see the abnormally high reservoir pressure, and this is allows for us to increase the mud weight to avoid kicks in low part of well and drill well successfully. So real-time drilling, geomechanics real-time drilling in drilling allowed to drill exploration well without any problem using pore pressure prediction. So losses risk in reservoirs from PP and SH-min decreasing were prevented too. And next tasks, this is mud losses prediction. This is vice versa by abnormal high pore pressure, and losses prediction can be associated with two factors. First factor, this is faults, and a crossing of faults during drilling can lead to mud losses. Also, this is stress pass effect. Stress pass effect, as you can see on this slide, associated with decreasing of pore pressure. If when pore pressure is decreasing, SH-min decreasing too. So in the depleted formation, we can see the mud losses. And And for example, if we drilled formation, not depleted formation 10 years ago for mud weight density 1.25 gram per cubic centimeter, in 10 years we cannot drill depleted formation with the same mud weight density, because using the same mud weight density, we will have already mud losses. So we need in the time decrease save mud weight window. This is a bright example of drilling risk map, and you can see on this drilling risk map main possible risk, technological and geological risks that can be provided in the drilling. They can be associated with breakouts, lost circulation, gas showings, stickings, and mechanical and differential stickings. For each type of drilling event, we can see the actions to avoid this drilling events, and prevention and avoiding, and a description of actions that we need to have if this case was happened. The next part of geomechanical tasks, this is borehole stability assessment. And please note this slide. I need to make the laser. Please see on this slide, and we can see the two type of mud weight. The blue line, this is static mud weight, and the green line, this is ACD, equivalent circulation density mud weight. When we are drilling, the static mud weight increased to value of ACD. It associated with grains of rocks and turbulent process and other processes that leads to increasing of this density. And if, for example, we have any faults during drilling, we can across by ACD, this is faults, and have mud losses. And so this is main factor to control ACD during drilling. And geomechanics makes this task. This controls allows us control ACD to avoid breakdown and mud losses, for example, during intersection with faults and fractures. After stop of drilling or back reaming out of hole, the ACD decreases to mud weight static value. And if you can see here, on the stage of back reaming out of hole, we can see breakouts. This is associated with decreasing of ACD to mud weight static. If on the drilling ACD doesn't intersect shear failure gradient, but on the back reaming out of hole, this is intersect this. And in the intervals where shear failure gradient more than mud weight static, we can see the breakouts on the caliper. Also, borehole stability, this is a time factor problem. The borehole breakouts increase greatly from the caliper locks, as you can see on this slide. And please see on these tracks. First track, this is drilling, 0 harrow, 0 hours, clear caliper, back reaming out of hole, increasing of breakouts, and wireline caliper, much increasing of caliper. So this is main task of this process, make uncased well as soon as less as possible, because as time, the extent of damage of borehole is increasing, and can be a problem. Also, real-time geomechanics for drilling can help us to predict the intervals of depleted pore pressure or abnormal high pore pressure, and make a decision to casing, for example, maybe to make decision to increasing or decreasing mud weight to avoid stickings, to avoid losses, and make rate of penetration faster. Let's see on the mud weight sensitivity. We must understand that distribution of principal stresses can be different. For example, in the normal fault, S1 will be vertical stress, S2 will be maximum horizontal stress, and S3 will be minimum horizontal stress. From this depend the distribution of mud weight from case to case. For example, for a normal fault, as you can see here, the most stability well will be associated with vertical well, or the well slightly inclined in the direction of SH mean. If we can see on the strike slip, in this case, the most instability well will be vertical well, but the most stability well will be associated with 4 directions. You can see here violet. On the left part, you can see breakout stereonet. On the right part, you can see breakdown stereonet. Stereonet allows you estimate mud weight depending on azimuth and deviation. On the radial, you can see circular, you can see azimuth, but this circle, this is deviation. And color, this is mud weight. Safe mud weight to avoid breakouts, and safe mud weight to avoid breakdown. And at last, this is thrust fault or reverse fault. The most stability well will be associated with horizontal well in direction of SH max. This is a reverse case related to relation to normal fault. And geomechanics takes into account these factors and allows us use correct safe mud weight window. And this is one of the methods to estimate the mud weight sensitivity. This is a real case. We can see on this stereonet, for example, that built for the same seal formation for these wells. The green points, this is safe wells, the wells that drilled safely. This is yellow points, this is moderate risk, and red points is this is high risk and high breakouts. And from the stereonet distribution on this slide, we can see that green points associated with center of stereonet, and red points associated with boundary stereonet. From this, we can make a conclusion that our stress regime is likely that this is normal fault, because we can see characteristics that characterized only for normal fault, not for strike slip or not for reverse fault. And so this is very important types of calibration of model using the same formation. For example, it can be shales, maybe shale layer that this is intersects all those wells on the oil field, or another types. The next part of tasks of geomechanics, this is hydraulic fracturing optimization. And geomechanics, this is a source of information for hydraulic fracturing. for hydraulic fracturing construction, we need for Young modulus, Poisson ratio, SH mean, and permeability. Using these parameters, we can estimate the height of fracture, width of fracture, geometry of fracture, and other parameters. If you can see on the slide, we can see that for hydraulic fracturing for optimization of injection wells were completed, and from this slide, we can see that out-of-zone injection wasn't found out. Maximum operational injection pressure were estimated, and this is absence of friction effects in this well. On the left part of slide, this is DTS, distributive temperature sensor. This is calibration factor for this optimization of height of hydraulic fracture. Unconventional reservoirs, this is area where geomechanics uses to. In terms of unconventional reservoirs, we need to understand where we need search the intervals for hydraulic fracturing. And geomechanics allows us to select most brittle intervals and more ductile intervals to make hydraulic fracturing in the brittle intervals, and assess ductile intervals as barriers of fracturing. This is example of 𝗚𝗲𝗰𝗵 formation in the Western Siberia, and selection of most brittle intervals in the silica and carbonates interval, and all another intervals, blue and green. This is intervals associated mostly with highly total organic intervals and highly shale intervals. Casing structural integrity, this is a very big problem, especially in high seismic regions. This is can lead to loss of well. This can lead to decreasing of production of oil and gas, and we need to have a decision to solve this problem. So geomechanic, especially 3D and 4D geomechanics, can work with the problem, and on the stage of modeling, we need to use the parameters of steel, the parameters of casings, to predict in which pressures and which stresses we can see the structural damage of casings. The next part of geomechanical, this is fault reactivation analysis and DFN reactivation analysis. Why it's very important? Because we know that when the injection is on the well, injection process lead to shift of more circles on the left side, and shifting of more circles on the left side can lead to intersection of this more circle by failure criteria, and this is can lead to failure and reactivate the fault. After faulting reactivating, the possibility of fault of mud weight losses during drilling is very increased. And to avoid this, we need to understand in the which the maximum allowable injection pressure we need to have. And for these purposes, making the fault reactivation analysis. The same for DFN reactivation analysis. Please see on this slide. On the case number 1, on the left side, water injection rate, medium average water injection rate on the field 22.500 surface cubical meters today. And on the case number 2, average water injection rates 50,000 surface meters cubic on the day. And due to this slide, we can see conclusion that also we can select the optimal water injection rate to avoid DFN reactivation and to avoid fault reactivation. Also, the sand production prediction. This is very dangerous event, especially on the fields where we have unconsolidated clastic rocks. And this is example of using of geomechanical modeling for sand production prediction in the time. Please see on this slide. You can see the combined pressure gradients and sand flood. Using geomechanical modeling, we can predict the time and year when there will be sand production. It's very important because each company operator need to understand in which time the problem of sand production will be more actual. Because sand production prediction causes the erosion of facility and equipment, causes the decreasing of, for example, gas production, oil production, and this can be lead to ecological problems too. So sand production prediction, this is really one of the most important factors to use geomechanics for avoiding with this. And this is the same, but only for any layer in the time. This is triangle of sand production prediction. On this axis, you can see the pore pressure. On this axis, you can see bottom hole pressure. And in the time, we can see the changing of border of most safe sand production and big risk of sand production. For example, on these years, 2008 was no sand. After 2015, there were sand mark and transient sand. And this is example of calculation of maximum bottom hole pressure to avoid sand production prediction. Please see on this StereoNet. StereoNet shows the location of point on the deviation and azimuth. This is SH mean direction and this is SH max direction. If we can see on the SH max points, SH mean points, sorry, there we can see that our map is most on green. This means that for direction of SH mean required less maximum bottom hole pressure calculation to avoid sand production. On the other hand, in the terms of SH max direction, we can see the most of red zones. It means that for avoiding of sand production prediction, we need more maximum bottom hole pressure. And also geomechanics allows us to correctly select commonly used techniques for completion. This can be cased hole selected and selective oriented perforation, cased hole gravel packs, cased hole fracking packs, open hole screens, open hole expandable screens, open hole gravel packs. There are very important task. This is a daily surface and shear floor subsidence as an reservoir and seal compaction. It very actually, especially in conditions of offshore fields, when we need to understand the subsidence of platform to avoid incline of platform or subsidence of platform. The bright example of subsidence of platform was North Sea. To do this, we need to build a 4D geomechanical model. The example of this calculation you can see on this slide. on the map, changing maps. This is Z rock displacement by vertical. This is intersection with vertical displacement, and this is chart calibrating on the GPS measurements. On the platform, we're setting GPS measurement, and using GPS measurement and data from our model, we can calibrate them each other and make prediction on the next years. Also, very modern direction of using geomechanics nowadays. This is carbon capture and storage, CCS. Why it's very important? Because utilizing of dioxide is very important for today. This is utilizing underground. This is one of the most single actionable acts to make it. And to do it correctly, we need correctly estimate the parameters of utilized reservoir, estimate the fracture strengths of seal, properties of reservoir to avoid, for example, of uplift, to avoid fault reactivation, fracturing, and another parameters to avoid breakthrough of dioxide carbon on the surface. Also, geomechanics allows us use correctly select the properties of well to avoid breakthrough by the well of dioxide on the surface. And also very important, this is seal integrity. Seal integrity, it can be in the estimated in the injection wells. You can see the bright example on this slide. And correct geomechanical model allows to estimate maximum allowable injection pressure to avoid breakthrough and out of zone injection from reservoir to seals, and avoid breakthrough of water injection, for example, on the sea, and make correct well injection only for target reservoir. Okay, thank you for attention. Please, questions.
If you have any question, you can open your microphone and make the question, or also you can write it in the chat. Yes, there we have a question.
Can you elaborate a bit, especially remembering? Yes, we can select a bit depending on casing, and recommend the most corrected casing by analyzing of drilling of previous wells, of course.
Thank you. Thank you so much for the question. Thank you all for attending today's webinar. It was a pleasure having you with us, and I hope you found
I have a question. I have a question written there regarding
yes. Thank you. You can go.
Regarding carbon capture storage. Can you elaborate a bit, especially regarding its quantitative model of the failure of rock? Thank you, Ivan.
Yeah, I answered this question already. Of course, so we can select a bit using experience of drilling of previous well, and make recommendations for optimization of construction of casing. Oh, yeah.
Okay, thank you.
Sure, one moment. I need to quickly translate the questions to quickly answer. How do we know the overburden pressure we made is correct? So it's very good question. How can I do it? Usually I use not only density log, I use also empirical correlation associated with true vertical depth of true vertical depth sub-sea, and compare density log overburden pressure and TVD correlation for overburden pressure, and two these parameters between them. And this is one of the single methods to understand that under overburden pressure is correct. What is the validation of collapse pressure and how do we know it's correct? The validation of collapse pressure usually uses by microimagers or caliper. But before we will make a checking of and calibration of collapse pressure, we need to understand that we have breakouts because the caliper can show us as K-seats and washouts and other types of damage on the well. And also we need to understand that we have breakouts, and after this we can use a caliper to validate the collapse pressure. Collapse pressure, this is a shear failure pressure. This is maximum allowable pressure. When if we will have mud weight low, that collapse pressure, we will have breakouts. If our mud weight will be more than collapse pressure, there will no breakouts. First question. There are many coefficients in the modeling data input, and I am confused about how to determine this. Tutorial trial and error method until the calibration data is correct. Yes, it's really usually how can we do it? Usually we are not modeling one well. We are modeling, for example, 10 wells simultaneously, and having statistic for these 2 wells, we can understand vector of our actions. And after, as you can see, the trial and error method, only this is only correct method. You are right. Use more statistics. Use not one model. Use, for example, 10 wells for modeling. In Lita Studio software, is it possible and to do batch hole correction using caliper and bit size on the shell line? Yes, of course, it's available. You can correct logs, for example, on caliper. You can correct acoustic density log and make bit size on shell line, of course. Okay, next question. What models are you considering for borehole stability? Only elastic and for elastic and no plastic? We can usually we can use elastic failure criteria, MegaPlus O&G, �𝗲𝗃, and another failure criteria. But for example, for unconsolidated formation, for example, Cinnamonian in Western Siberia, we can use plastic formation cup model because this is a very difficult formation in terms of drilling, and the elastic model, elastic borehole stability doesn't work in this unconsolidated formation. Can we have 1D geomechanics workflow webinar in future? Not
Sure.
correct. Not understand. Not clear question. Webinar. Yes. Of course. We can provide it. No problem. I can prepare to this. Sorry. Yes. We can have. Do you have experience in geomechanics for geothermal projects? I'm sorry, no, I have not experience because in the Russian Federation this is not actual direction. The geothermal projects are not actual now in our country, so I have not experience. But if I will have a possibility to make it, I will be very glad. So thank you for your question. Do you have experience? Yeah, it's the same question. How to choose when we can use more column criteria, some depth range, and use other failure criteria, Hoek-Brown, for deeper depths? Can you share experience using this criterion? First method to understand which criterion you can use, more column or Hoek-Brown, you can build the 2D charts, as you can see in the 𝗚𝗲𝗂𝗃 monography. He showed us the charts where he built a correlation between sigma-3 and sigma-1 and estimate configuration of points of failure and understand which criterion do you need. More column, maybe ladder, maybe another. And second type of selection of criteria, calculate, for example, 3 or 4 distribution of this criteria and select which of them is the best for you in terms of caliper, in terms of microimager and another. Do you provide real-time geomechanical support for drilling using your models? What is the drilling efficiency when using geomechanics? Yes, we can provide it. As for drilling efficiency, this is usually optimization of mud weight window in the difficult formation, especially shale, especially fractured formation, because we can select conditions for drilling of this problem formation at any angle and optimize the process of drilling. The benefit of geomechanics in this case, this is optimization of costs for mud weight. How we can develop CCS in the geomechanical analysis? We can make a 4D geomechanical model and estimate the condition of CCS. For example, we can model the injection rate of CCS. We can model the strengths and elastic properties of seal of reservoir and estimate the uplift during the CCS. We can estimate potential for fault reactivation, DFN reactivation, and another processes. What is your approach to determine epsilon values and BO coefficients for minimum maximum stress for elastic model? Yeah, thank you for your question. This is very difficult question, yes, because we have very often we have not any field parameters that can help make this, and often how we can do it. We, for example, have XLOT data, fracture closure pressure. Having the fracture closure pressure, we know the SH mean. So we need iterate epsilon values and epsilon values so that our SH mean profile will according to XLOT data. As for BO coefficients, we can estimate it from laboratory condition. Thank you for your questions.
Yes. Thank you for the questions, and so also thank you, Dr. Jan, for the answers.
Sure. If you will have more questions, please write me in LinkedIn or write in the WhatsApp chat. I will answer for all your questions. Thank you.
Thanks. Okay, so I think we don't have more questions. Yes, so again, thank you for all attending today, also for making all the questions. It was really nice to have you here in the webinar. I hope you found the session both insightful and engaging. Special thanks to Dr. Yen for leading such a valuable discussion, also for answering all the questions to the attendees. If you couldn't join us today, don't worry, because we are recording this webinar and it will be available soon for you. We can send you the link. Also, you can find this webinar in our channel, in YouTube channel, so you can find it there. So yes, we truly appreciate your participation and look forward to seeing you in a future session. Thank you so much, everybody, and have a good day.
Thank you, dear colleagues. Have a nice day. Have a nice evening.